Knowing that quantum mechanics has something to do with explaining the interactions of light and matter, for instance, in the context of the photoelectric effect, or black-body radiation, or bright line spectra of atoms and molecules, one might be led to the question of when is quantum mechanics actually relevant? The domain of quantum mechanics is unfortunately not a particularly simple question. When does it apply? Well, on the one hand, you have classical physics, and on the other hand, you have quantum physics. And the boundary between them is not really all that clear. On the classical side, you have things that are certain, whereas on the quantum side, you have things that are uncertain. What that means in the context of physics is that on the classical side, things are predictable. They may be chaotic and difficult to predict, but in principle they can be predicted. While on the quantum side, things are predictable too, but with a caveat. In the classical side, you determine everything. Basically, every property of the system can be known with perfect precision, whereas in quantum mechanics what you predict are probabilities. And learning to work with probabilities is going to be the first step to getting comfortable with quantum mechanics. The boundary between these two realms, when the uncertain and probabilistic effects of quantum mechanics start to become relevant, is really a dividing line between things that are large and things that are small. And that's not a particularly precise way of stating things. Doing things more mathematically, quantum mechanics applies, for instance, when angular momentum L is on the scale of Planck's constant, or the reduced Planck's constant, h bar. Now, h bar is the fundamental scale of quantum mechanics, and it appears not only in the context of angular momentum. Planck's constant has units of angular momentum, so if your angular momentum is of order Planck's constant or smaller, you're in the domain of quantum mechanics. We'll learn more about uncertainty principles later as well, but uncertainties in this context have to do with products of uncertainties. For instance, the uncertainty in the momentum of a particle times the uncertainty in the position of the particle. This, if it's comparable to Planck's constant, is also going to give you the realm of quantum mechanics. Energy and time also have an uncertainty relation, again, approximately equal to Planck's constant. Most fundamentally, the classical action, when you get into more advanced studies of classical mechanics, you'll learn about a quantity called the action, which has to do with the path a system takes as it evolves in space and time. If the action of the system is of order Planck's constant, then you're in the quantum mechanical domain. Now, Planck's constant is a really small number. It's 1.05 times 10 to the negative 34 kilogram meter squared per second. Times 10 to the negative 34 is a small number. So if we have really small numbers, then we're in the domain of quantum mechanics. In practice, these guys are the most useful, whereas this is the most fundamental. But we're more interested in useful things than we are in fundamental things, after all. For example, the electron in the hydrogen atom. Now, you know from looking at the bright line spectra that this should be in the domain of quantum mechanics. But how can we tell? Well, to use one of the uncertainty principles as a calculation, consider the energy. The energy of an electron in a hydrogen atom is, let's say about 10 electron volts. If we say that's p squared over 2m, using the classical kinetic energy relation between momentum and kinetic energy, that tells us that the momentum, p, is going to be about 1.7 times 10 to the minus 24th kilogram meter kilogram, where'd it go? Where's my eraser? Kilogram meters per second. Now, this suggests that the momentum of the electron is, non-zero. But if the hydrogen atom itself is not moving, we know the average momentum of the electron is 0. So if the momentum of the electron is going to be 0 with still some momentum being given to the electron, this is more the uncertainty in the electron momentum than the electron momentum itself. The next quantity, if we're looking at the uncertainty relation between momentum and position, is we need to know the size of, or the uncertainty in the position of the electron, which has to do with the size of the atom. Now, the size of the atom, that's about 0.1 nanometers, which, if you don't remember the conversion from nanometers, is 10 to the minus 10th meters. So let's treat this as delta x, our uncertainty in position, because we don't really know where the electron is within the atom, so this is a reasonable guess at the uncertainty. Now, if we calculate these two things together, delta p, delta x, you get something, and I should say this is approximate because this is very approximate, 1.7 times 10 to the negative 34th, and if you plug through the units, it's kilogram meter squared per second. This is about equal to h bar. So this tells us that quantum mechanics is definitely important here. We have to do some quantum in order to understand this system. As an example of another small object that might have quantum mechanics relevant to it, this is one that we would actually have to do a calculation. I don't know intuitively whether a speck of dust in a light breeze is in the realm of quantum mechanics or classical physics. Now, I went online and looked up some numbers. For a speck of dust, let's say the mass is about 10 to the minus 6th kilograms, a microgram. It has a velocity in this light breeze of, let's say, 1 meter per second. And let me make myself some more space here. The size of this speck of dust is going to be about 10 to the minus 5 meters. So these are the basic parameters of this speck of dust in a light breeze. Now we can do some calculations with this. For instance, momentum. Well, the momentum is just the mass times the velocity. So P is going to be about equal to 10 to the minus 9 kilogram meters per second. Better make that 10 to the minus 6th kilogram meters per second. My notes are backwards here. The uncertainty in the momentum then is, we could say it's 10 to the minus 6th kilogram meters per second, but let's say it's a little smaller than 10 to the minus 6 kilogram meters per second. Let's say 10 to the minus 8 kilogram meters per second. Now the position uncertainty that's going to be a function of the size of the object. If we know the size of the object, the position uncertainty is probably not all that much larger than the size of the object. In fact, it's probably smaller. We can measure where a speck of dust is to better than the diameter of the speck of dust, just by putting it in a microscope, for example. So let's say the position uncertainty here is going to be about 10 to the minus 6th meters. Now if we run that calculation, delta p, delta x, comes out to be 10 to the 6th times 10 to the minus 8th, which is 10 to the minus 14th kilogram meters squared per second. This is a good factor of 10 to the 20th larger than h bar. So this is solidly in the realm of classical physics. So even something really small, like a speck of dust in a light breeze, is still going to be classical. So the size of something here, the smallness of it, is something that you might have to calculate until you start getting a feel for it. Just some basic examples to put things in context a little further. Quantum mechanics is most likely going to be important if you're dealing with single particles, atoms, molecules, single electrons, single photons, small systems of electrons and photons. It's also going to be very, very relevant if you're talking about semiconductors. The quantum mechanical properties of semiconductors are what makes them into such spectacularly useful electronic devices. Lasers are another situation where quantum mechanics is crucially important. Without quantum mechanics, there would be no lasers. And finally, if you're talking about very low temperature physics, temperatures less than about 100 Kelvin, well, those are going to be quantum mechanical as well. So single particles, weird materials, crystals, lasers, low temperatures, they're kind of an exotic set of phenomena, but we're adding more all the time. Quantum mechanics allows us to do things that we wouldn't be able to do in the classical world. Consequently, it's in our best interest to try and push quantum mechanics as far as we can take it. So, to check your understanding, this is a short question about the uncertainty in, the relevant parameters of interaction between two helium atoms, and what temperature scale these interactions become important, or become quantum mechanical at. One might be led to the question of when is quantum mechanics actually relevant? The domain of quantum mechanics is unfortunately not a particularly simple question. When does it apply? Well, on the one hand, you have classical physics. Knowing that quantum mechanics has something to do with explaining the interactions of light and matter, for instance, in the context of the photoelectric effect, or black-body radiation, or bright line spectra of atoms and molecules. On the other side, things are predictable too, but with a caveat. In the classical side, you determine everything. Basically, on the quantum side, you have things that are uncertain. What that means in the context of physics is that on the classical side, things are predictable. They may be chaotic and difficult to predict, but in principle they can be predicted. Well, on the quantum, and on the other hand, you have quantum physics. And the boundary between them is not really all that clear. On the classical side, you have things that are certain, whereas on the quantum